In video 4, we're going to take a look at some machine learning models in action, including we're going to look at an open Kaggle contest and see how we can do with some of those models. Before we get into that, let's frame how we got to this point. So we've been looking a lot at tabular data. Tabular data, you have a number of n samples, you have d attributes. Generally in supervised learning, you're trying to predict a target attribute. So any arbitrary piece of data in the table or matrix, so highlighted by the red square there, you can look at that and understand what the context is. So if your samples are people and the attribute is height, 6'1", I can understand that piece of information. When we get into other types of machine learning and AI, we're going to have other types of data. So I'm shown here. So language data is a type of sequential data. If I just gave you the word jumped, it wouldn't mean anything, but in the context of this sentence, the quick brown fox jumped over the log, it has meaning. It has meaning because it's in a sequence of words. Likewise, with image data, it's really two-dimensional information about the color of pixels. And so here you can see if I just gave you one individual pixel, it would be meaningless. It only makes sense in the context of the two-dimensional space around it. So when we get into those other types of data, we're going to get into more neural networks. But in this video, we're going to focus on some more traditional machine learning models that work really well with tabular data. We'll talk about we'll talk about neural networks briefly, but we're going to see some of these models in action. As a quick review, here's what an example of tabular data might look like. This is information about emails. I've got two input features, number of keywords that are identified as often associated with spam, number of links and attachments. And then this is a classification problem. So we have a discrete target variable. In this case, it's just a binary classifier. Is this email spam or not? And remember that it's really super important that all of our data samples, they need to be independent of each other. And then identically distributed, mean they're randomly drawn from a population so that we don't skew our data. Like, for example, we don't want all emails from the same sender. We want to get a good representative example, and then these statistical models will be their most effective. Okay, so a machine learning model, we've talked about it as represented as a function that takes an input x being some set of inputs, and we're going to get an answer y, our output. And there's two types of parameters I want to call out. There's hyperparameters, and those are configurations that are set or determined by the engineer. A human decides that, the person modifying or creating the system. Then there are typically what you're probably used to hearing about when you hear about the most recent language model has this many billion parameters. Those parameters are model parameters, and those are learned. The value of those is learned through a training process. So I want to distinguish between that. We'll see the difference in a couple of the examples we're going to look at. Something else I've focused on a lot in this course is thinking about the data from a geometric view. So we can think about it from the pure numbers or algebra or math, I guess, point of view. But the geometric view really helps us to understand what these models are doing. So we've already talked about linear regression, where the model tries to find the best fit line for the data. Okay, so let's talk about now regression versus classification. In a regression problem, we're trying to predict or determine what the output of a continuous variable is. So let's say we're trying to predict what the temperature will be tomorrow at noon. Okay, so we're looking to predict a specific value, and that's indicated by this dashed line. The regression in green there, that point is we're going to have a prediction in a linear model. We're going to end up predicting some point on our line based on the input attributes. Now think about a classification problem. So in a classification, I want to take some set of information, our input, and determine which class is it. Is it red or blue in this case? That's a binary classification. There's only two choices. And so in that type of a model, logistic regression would be a model that's used for this, one basic example. And then in that case, we're trying to take our input and figure out, okay, which side of that line does it fall on? And if it falls above the line in this case, we're going to say, okay, that's our class one. This is a red instance. Or if it's below, it's blue. So in the linear model, we're still trying to come up with what's the best fit line. And I'm showing you two dimensions. So this works in higher dimensions. In higher dimensions, it's a hyperplane. So if you think about in 2 dimensions, I just need a one-dimensional line to separate. If you think about 3 dimensions, so just like the space of the room around you, I can take any arbitrary 2-dimensional space. So here's a sheet of paper, every point in this room is either above or below this piece of paper. So the number of dimensions you have minus 1 is the size or the dimensionality of your hyperplane. But it's easier to think about in 2D to reason about, so we use those examples. So that's what a linear model is doing. And we also talked about most of the world does not fit into a linear model. It's often much more complicated than that. So we look for the best model that will fit our data. And here's an example of, if let's say we were given the first 4 data points in training and we used a nonlinear model, a cubic model, you can see the red line fits those training points perfectly. However, when you then at test time see those 2 data points on the right, it's going to do a bad job of predicting those. So in this case, a linear model would have done better. But that's always the challenge. Finding the best fit for your training data may not always be the best thing for all the rest of the data that you haven't seen. And so when you're training models, you often take your data and you split, let's say take 80% and train just on that 80% and then evaluate on the other 20. And you can do different splits. There's lots of different approaches to do that. But that's part of the technique you can use to find what's the best model that implements that function for my data with the best accuracy, or whatever evaluation metric you're using. Okay, so let's continue with the predicting the temperature approach. So you've got your data matrix, and remember we're going to take data in batches. So we talked about that in an earlier video, so that helps us train more efficiently and also deal with large amounts of data that we can't all process all at the same time. So you've got your data matrix, and in supervised learning, you've got the Y, which is the actual temperature. I'm not calling out the individual attributes here. They could be anything. It could be what's the temperature right now, what's the barometric pressure, the time of year, all that kind of stuff. We're not going to worry about that. For right now, we're just focused on the model is predicting that Y column is actual. That's what the model actually predicted for these samples. And then, the Y predicted is the far right column. And then you can see the actual, that came from our training data. So what we want to look at for this batch is how big is our error? And then based on that, how do we adjust our model parameters to better fit this data? At first you might think, okay, well, let's take the delta. We subtract our actual minus predicted, and then that gives us our error, which you can see here in the blue column. And if you add up the error for this batch, the total is 2.4. So we want to, you often look at the average, right? So on average, what was my error for each of the samples in this batch? So I was off by 0.48. In terms of degrees, we can say, okay, that sounds pretty good. But there is a flaw with this approach, because just by adding up those numbers, sometimes we have a prediction that's less than the actual, and sometimes it's greater. So if you just add the numbers, you're underrepresenting what our error is. So one approach then to fix that is, okay, well, let's take the absolute value. So basically remove all the negative signs. So if you take the absolute value and add all those up, now you've actually got 4.6. And even though when you initially look at these numbers, they look pretty small, you can see we really underrepresented the error, because the average almost doubled our average error per prediction when we take the absolute. So that's an important concept to remember. Now, actually, a common technique is not just to take the mean absolute error, but take the mean squared error. So the mean squared error, MSE, is a very popular loss function or objective to use for a regression problem in machine learning. So if we square all of those errors, so squaring has 2 benefits. It makes everything a positive number, first of all. So we also accomplish that with our absolute, taking the absolute value. But it also is going to more heavily penalize errors, or I should say predictions, that are farther off the mark. So if you take the MSE, you're going to see the sum of all the squares is 8.82, so 1.76. So it actually, our average error is worse than, according to the MSE metric, than just by taking the absolute. And what does that tell our model? It tells our model that it can make a bigger, remember we talked about nudging the model parameters in the right direction toward being more accurate or more correct. So the fact that this is a little bit larger MSE, it can take a bigger nudge. We can take a bigger step forward and feel confident that we're not going to overstep where it is that we really want to go. Sometimes you'll also see a metric SSE, so just the sum of the squared error. So if you just want to take the aggregate, you care about the magnitude of the total error. If that's the more important aspect, you might use SSE. And then in that case, you just simply wouldn't divide by a number of samples. In order to understand why the squared error is better, it helps to look at this graph. So the blue is the squared error. And you can see that, so 0, if you were right at x0, that would be your error 0. There is no error, and you've made perfect predictions. We'd all love to be there, right? So you can either be, and actually once you get to the squared, you're only going to be on the right half of this diagram. So focus on the right side, but I'm comparing the squared to the absolute error. So you can see as your error gets bigger, you get a much bigger penalty. And so you know to take a bigger step in the right direction. And actually this is where calculus comes in, because at any point on this blue line, I can take the derivative, and that tells me the slope, and that tells me in what direction. If the slope is 0, that means I'm at x equals 0, I've got no error. But if it's a really steep, that means I'm somewhere up here in the graph. I can take a big step forward. Whereas once I get closer to, approximating the actual answers, I can take smaller steps forward because I'm getting close. I don't want to overstep. And so this is why the squared error is pretty helpful in machine learning. Okay, let's talk about our first new model that we haven't seen yet. So a decision tree. Decision trees are interesting because here's an example, just a conceptual example of one. It's just a series of questions, and you either go to the left or to the right in the tree until you get down to the very bottom, which would be called a leaf node. And now you're at your answer. Now this mirrors or mimics how we do explicit programming in traditional software. If this is the case, do something. Otherwise, if this is the case, do something else. The difference is in machine learning and in decision trees, no one's explicitly writing these rules. The model is going through the data, looking for where is the most information I can gain by splitting based on some criteria, and continuing to do that until it gets at each leaf node, I've got all of the items that look pretty similar or hopefully are the same. And then it continues to do that until it's classified or put all of the information into the tree to satisfy some criteria. You can actually do this both for classification and for regression problems, but it's a surprisingly effective technique. The one thing to say about this is it is very susceptible or sensitive to the order in which the data is fed to it, the order of the data in the batches. Because if you think about it, whatever decision you make at the top of the tree, whatever criteria, that's going to affect everything below it. Is very important. So you can there are algorithms to look at restructuring, balancing, making more intelligent decisions. But generally speaking, there's some sensitivity to the specific order and just how it happens to fall out. But let's first better understand what this decision tree is actually doing. So from a geometric perspective, it helps. I always feel like that's a good way to understand. So this is just some arbitrary data points. We've got a class again that's red and one that's blue. And you can see by looking at the geometry of this, a linear model is not gonna suffice. I can't draw a line or more generally a hyperplane and separate these two classes. So we're gonna use a decision tree. We're going to give this data to that model and see what it does. Now, when I ran a decision tree using the scikit-learn library, this is actually the model that it created. So you can see it's first separating based on the value of y, then it compares x, and actually already at that first branch point, you can see that it says, okay, well, everything that's less than the value of 13.75 on the y-axis, we already know is blue. But then there's a lot of other subcategories. In general, you want to make the tree a more shallow depth. Sometimes you can't avoid that. But one nice thing about decision trees is they are somewhat explainable. I can look at the model, the structure, and kind of understand, generally speaking, what's going on. In a very large tree, it can get difficult, but I can at least have some idea and look at it and know, okay, here's generally speaking what it's doing. So now here's the geometric interpretation of what happened. And this is where you can see it's basically carving up the geometric space into these different sections. So look at the top here. Everything above the 13, everything over there is blue. That was our first divider. If you remember, the root node of our tree, it first said if it's less than 13, continue on. Above 13, I already know it's blue. And you can see the decision tree handles this non-linear aspect of our data pretty well, because it's just going to arbitrarily keep dividing up sections until it's, it's met either its constraint, which is don't branch so many levels, or, constrain the model in some other way, or it's going to continue until it can carve up enough little sections to successfully classify or do the best that it can at each one of these. So it's helpful to think this is where the geometric view really comes in handy. So let's put these decision trees to use. I went on Kaggle. Kaggle's a website that has machine learning and AI. You can run notebooks. They have existing code and competition. So here's a competition. I just went and looked, found one. This is something I don't know a whole lot about, but it's looking at predicting the properties of polymer substances. And there's some information about it here. There are, I believe, cash prizes for this. So the training data, if you look here, it's got training data, so there's an identifier. And then here, this smiles is a format that's going to give you, I'll show you a string representation of what the chemical structure is. And then there's actually 5 target variables, and there's a lot of data, a lot of the rows are missing values for some of these, so it's kind of difficult to create a model that predicts all 5 at once. So I'm going to focus on just this FFV, fractional free volume, has a lot of the data populated. So given this smiles, and here let me show you. So here is this string representation, which probably doesn't make a whole lot of sense to you. I know it doesn't to me, but there is a Python library, RD kit, that will parse this and will pull out the data, and it gives you information about this molecular structure. Just briefly, here's an example of a molecular structure, and you can see how it takes the atoms and their connections and the different properties, and it represents that as a graph, which then they turn into a string format. So just give you a sense of what we're actually looking at here. Now we're looking at a Python notebook that I've put together to process and try to create a decision model to see if we can accurately predict that FFV variable. And here's a usage of this RD kit library that I was talking about. So I'm just giving it one of the samples from the data, and it first shows a visual representation of the molecular structure, but you can get all of the information from it. And we'll use that. The part of the challenge then is figuring out what features. How do we represent this molecular data as features for our model? So first, we're going to read in our data. And there's actually almost 8,000 samples, and we have 7 attributes. So here, this is these first 7, I should say, are the data that we read in from the training file. And then what we've done is we've used this library to parse this smiles data, and that gives us an object back which holds all of that information in a format, in a Python object, and we can do more with it. So we've got this molecular structure object, and one of the main things you can do is you can get a fingerprint from it. The fingerprint is it's a bit vector of 2048 bits that have different information. So it's kind of a shorthand way to get a lot of key information about it, but that doesn't tell you everything. So we'll also grab the molecular weight and the number, these different attributes about number of electrons and things like that. So we will grab all of that. That's not everything, but that's a good amount of the information, and include that as features in our training data set. So you can see here, what it actually gives you for this fingerprint is this explicit bit vector object, and it's got each one has 2K of bits, and here's the first 20. So it's just zeros and ones, and each of those positions tells you something about that molecular structure. Okay, this is an evaluation helper method, and it's going to give us some basic metrics. So here we're going to split the data like I mentioned. So we've got this training data set. We're going to use 80% to train the model and the other 20% to test and validate along the way. How are we doing? And you can see, so we've split up our almost 8,000. So that gives us 5,600 training samples, and then we can validate it against these 1,400 test samples. Some of the models perform better when you scale the data, so we'll set it up so we have scaled data as well. All right, to start with, we've looked at linear regression in the past. I want to just show you how this will do, and to no one's surprise, it's not going to do very well on here. So now we've got our linear regression model. We did use the scaled data, and now I've got this is the method to evaluate it. So let's evaluate how we did. Okay, our R-squared score is very bad. The mean squared error is really low. So if you look at that at first glance, you might think, oh wow, we're doing pretty well. So let's take a look again at, just as a reminder of how we interpret this R squared. So 0.3, and if you look at that, it's really anything below 0.5 is a pretty weak fit. You want to get to 1. And so we're not really capturing the variance that's in our data. And if you look at the, what are the outputs? And here you can see, like, look, there's a small variance between some of these. So 0.0007 is actually significant when you look at what are the values that we're talking about. And this is why we do the exploratory data analysis up front. So if we look at the distribution of this, you can see it all is within a pretty small range. So even being off by those fractional amounts really contributes to our error rate and our accuracy. Okay, so the linear model didn't do very well, but we've just been talking about decision trees. So decision tree regressor is a model implemented by scikit-learn that does regression using the decision tree. So let's see how it does. And you can see it is doing quite a bit better. So there are some nonlinear relationships in our data. 0.5, if we recall, 0.5 is, okay, a moderate fit. So we're doing a lot better than the linear model. Here we're capturing some of the trends, but certainly not all of them. And let's also take a look. You can see there are some methods in here to just show you the tree. So let's take a look at the tree itself. And we didn't put any constraints on it in terms of the depth of the tree. So this could basically keep creating branches until it can adequately have leaf nodes that capture, or the leaf nodes hold similar items. So let's see what this produces. And here is our decision tree. It is so, let's see, it looks maybe about 20 levels deep. There are so many branches at this resolution, we can't even see what the individual nodes are. So it would be much, or I should say, pretty difficult to interpret what's going on here, but you could inspect aspects of this and figure out, okay, what's actually happening. And this is how the decision tree is actually working. Now, generally speaking, people don't use just an individual decision tree. So why is that? We talked about the fact that the order of the data is sensitive to that, and you could get many different decision trees based on how you slice and dice the data. Okay, so a technique that people use in a common model is called random forest. A random forest is an ensemble model, so it takes a number of smaller models. Generally, each individual model may be not as strong, but then it runs all of those and it looks at all of their outputs, and then in using some algorithm, oftentimes a majority voting decides, okay, well, if the majority of these models all predict the same thing, then that's a likely outcome. So here's our random forest regressor, and we can run that, and notice we're saying the number of estimators. So this 100 is a parameter saying create 100 different individual decision trees, and for each one, it's going to randomly split up the data, and it's going to organize the data in some different way so that each of them gets, I guess, a different take on the data. And that will give us hopefully a better chance in aggregate of predicting the right thing. So let's see how this random forest did. And you can see 0.679. So that did significantly better than just an individual decision tree. The mean squared error went down. I think our linear model was 0.007. Now we're down to 0.003. So random forest decision trees, these are surprisingly effective models, given if you think about it kind of, I don't want to say simplicity because there's some interesting things going on in that algorithm, but this gives you an idea of how they can be moderately effective. Really, we didn't do any too much work to begin with here. We prepared the data, we did scale the data. Actually, excuse me, for a decision tree and random forest, you don't need to scale the data because it's just going to carve up that input space. For models where you're looking at gradients and things like that, it does help to scale the data. So that's kind of a short introduction to decision tree. And then random forest, remember, is taking a number of decision trees, each one taking some random portion of the data, aggregating it in an ensemble model into a majority vote to get the best possible prediction. Let's take a quick step back and look at what these ensemble models are actually doing. So we're taking our training data on the left, taking different samples from that, and you can slice it and dice it different ways. We're training these smaller models, if you will, models 1 through n. Then our ensemble model, when we run the whole thing, it runs all of those models and then combines those individual answers into an overall answer in some way. I mentioned that majority voting is one way, so that would be actually more typically used in a classification problem. So which category or class am I predicting? In a case of regression, which we've been talking about, a continuous variable, another approach would be take all of those answers and then average them. And then that's actually what is our overall ensemble model prediction. The intuition here is the same as if you were trying to make a decision. You would probably talk to a number of people. You would try to find multiple experts in the field, get all of their opinions, and then kind of synthesize that to draw your own conclusion. That's really what is happening here. Random forest then is an ensemble model, but there are different types of ensemble models. A very popular and very effective one is XGBoost. So here I'm showing you the code for this. So we're going to use XGB regressor because we're predicting a continuous variable. We can do some work in parallel. And there's also something in here I haven't talked about yet. So grid search. So this is a way to try out different hyperparameters, kind of automate that process. And what this will do is it will do a training run with each of the combinations. In this case, I've only got one, but I could add other constraints, or excuse me, hyperparameters here, such as the max depth of the tree, etc. So here I'm going to run a grid search and use the values for number of estimators to be 100, 250, and 500. It's going to try out each of those and then report back to me which one is the best. So this code works similarly, and the XGB regressor is going to use decision trees underneath, but I'll explain in a minute how this works. You're going to see that this actually gives us the best performance of all of the models that we've looked at. So here you can see we've got 3 candidates, and it's running those in the background right now. Okay, so we can see we got an R-score of 0.75. That's actually the best that we've done on anything that we've tried so far. And you can also see that the number of estimators, so of these, the more estimators we had, the better we did. You will find that if you continue to add more, you're only going to get marginally better results on here. But it is quite interesting that this is more effective than the random forest. So here you're kind of echoing back. So the R-squared, the actual score we calculated, is slightly different, and the mean squared error is still 0.0003. I think that's similar to what we saw in random forest, but because we're talking such small differences here, we are getting a better coverage on this model. So XGBoost is a really popular library, and kind of out of the box, you can use it pretty effectively in many cases with tabular data. So in an ensemble method that uses boosting, here's kind of some intuition of what's actually happening. We take our original data, and here we're showing classifier, but this could be a regression model also. And we run that, we get an answer, and we have some error rate, and that's kind of this orange rectangle on the bottom. So that residual we carry forward to a secondary model, and that is a new problem. It's a smaller scale problem, if you will, and we train a model on that to solve for that. That, of course, leaves some residual error, and we continue to do that until we get to a point where we're satisfied that we're accurate enough, or we can't, it's not converging, we're not getting any better answers. This boosting technique can be extremely effective on tabular data, and XGBoost is a popular Python library to do that. I want to show you one last machine learning technique, which is an unsupervised learning technique, clustering. We're going to look at customer segmentation. So without any target labeling or specific work done to annotate our data, we're just going to take a set of customers and try to group them into related groups, in this case based on their spending. I have some data here, mall customer data. This is from another Kaggle website or project. I'll give you the link. Pretty simple. I believe it's synthetic. It's only got 200 rows or samples, and it's got the person's gender, age, income, and their spending score, which spending, of course, in this we're very interested in. But we're not going to do anything else with that other than right now we're going to cluster on just income and spending score. Remember, 2 dimensions is easier to reason about. And we're going to use k-means clustering. So the k means the number of clusters. What is the ideal number for k to start out with? Well, a priori, we don't know. But what I've just done is I've run the algorithm for the values of k 1 through 10. And then what we can do is plot that. And if we take a look, you can use what's called the elbow method. So this metric, by the way, this WCSS, it's a measure of how spread apart the values are in each cluster, or I should say the average distance from the center. So if you have a bigger number there, that means your cluster is more dispersed. It maybe has less meaning. You'd like to get that to a smaller number. So you can see with only one cluster, things are really far apart. as soon as you get to 2 clusters, things are getting closer together. And once you get to this elbow here, that's at k equals 5. You can see from 5 to 6, we're not getting much better. So 5 is probably a good place to stop. So we're going to go ahead and cluster with k equals 5. And we'll run that here. And let's visualize now what we've got. So here are our segments. Remember, they don't have names at this point because we just know they're grouped together. You can then go and look at, well, what is the distribution of the features within each of these clusters, and know, are they high spending, low spending, whatever your criteria is. So you can see in this case, this data based on these 2 parameters that we've looked at, it's pretty straightforward. The scales here are from small negative to positive because we've scaled the data first before we did this. That's why you're not seeing, more realistic like dollar value numbers. So here, we can also try doing this for, let's see what it looks like for k equals 3. And if we do that, okay, now these data points here, sort of in the middle, have kind of become part of this cluster over here. And when you do this, you can also see, we can look to see where the center points are. So the center points they call centroids. So in our k equals 3 run, you've got a center point middle left, and then top right and bottom right. So just to show you, here's an example where we're clustering on 3 of the properties in our data set. And so in a 3-dimensional cluster, you can view it like this. It starts to get a little more difficult to discern where the different groups are, but you still accomplish the same goal. And in terms of looking at the data, of course, the more relevant features that you're adding, the better clusters you're going to get. So just wanted to give you that quick view. I think I'm going to stop here. This video has gotten a little long, so I'll do neural networks in the next video. Hope you're enjoying this, and I'll see you in the next one. Bye.